the net point is there are many other circuit implementations which will allow you to optimize the delay of this full adder somehow, right? Unfortunately, there is only a certain amount of gain that you can get by optimizing the delay at a circuit level. Okay. So for example, if I am doing an addition in a server, it's a 128-bit machine. Just think about the fact, how much ever I optimize my delay at a circuit level, right? I reduce T sum and T carry to the maximum extent possible. Ultimately, the delay is going to be killed by N. When I want to do ripple addition of 128 bits, it's that N that is going to dominate the delay term and not T sum and T carry. So there's only certain amount that you should spend optimizing the circuit part of a full adder. Beyond the point, even if you have to do even a desktop machine, 32 bits, right? Now even that's 64 bits, right? GPUs, all of these are going to have larger bit registers. And in order to optimize that ripple carry delay, we have to optimize the architecture of addition. It's not possible to do it through circuit optimization anymore. Okay. So we will look at various architectures of adders going forward, and some of them we will cover in this class. Okay. So the first thing is called a carry skip adder. Okay. So the idea is essentially like this. Suppose I have an n-bit ripple adder. Okay. Full adder. Full adder. Suppose my aim was to just ensure that the final carry out came out as fast as possible. Okay. It should come out as fast as possible. The simplest thing to do, final carry out. Okay. Remember that if any one of the stages in between generates a carry, then you are done. The carry will appear much faster than the worst case critical path. Okay. So if I want to make sure that that worst case propagation is killed, right? All I have to do is take the propagate signals Pn-2, Pn-1, right? And create a signal called P equals product of Pk, 0 to n-1. Which means that if all the adders are in propagate mode, all I have to do to get the C out is to bypass the signal, bypass the entire adder path and take C into the output. Right? That's what propagate means. If every adder, that's why we're using an AND condition there. If every adder is in propagate mode, carry out equal to C in. Okay? So what you do is you simply put a multiplexer here. C in. This is my C out. And this multiplexer will be controlled by this propagate signal. If it is 0, this is 1. If it is 0, it means at least one adder in between was not in propagate mode. Which means that the carry is being generated somewhere in between, or the carry is being killed somewhere in between, and therefore you have to wait for the carry to propagate from there. Right? But if P happens to be 1, then C out is simply equal to C in. This way, all I am doing is, I am not saying that this adder is unconditionally faster. That worst case delay I have reduced. The worst case delay now, what is the worst case delay here, by the way? Tell me. At least in what mode should each of these N adders be in? if everything is in propagate mode, okay, if everything happens to be in propagate mode, that is this equal to 1, this equal to 1, then how long will the carry out take to settle? It's going to take 1 unit of time to create all the propagate signals. A XOR B operation will happen in parallel across all the adders. You will get all propagate signals in one shot. Then you just need to do this addition and multiplexing. In 2 units of time, or let's say 3 units of time, doesn't matter. In some fixed time which is independent of n, I have got my carry out ready. So it cannot be that everything is in propagate mode. First one is in generate mode. Exactly. So the worst case is this has to be in generate mode and then the carry has to propagate all through. Right? Clearly, I cannot do this for all the 128 bits because ultimately my worst case is, if you look at the second worst critical delay time, right? It will be the first one being in generate and everything, and now that is going to kill my time, my critical path. Therefore, I have to do something where this, even if one stage is generating, that propagation should not take enormously long amount of time. Okay? The second key point is, if this generates, if one stage generates, suppose I split my 128 bits into chunks of let's say 4 bits. Now, if a carry is generated in any one stage, then I don't have to wait for the carry to propagate all through. Okay, this is the key idea, but let me show you the schematic, then you will figure out what I am saying. Okay, so the idea is now to partition n bits into k bit segments. I think I used M in the slides, so let me use M bit segments, and create number of stages, therefore will simply be n by m. Okay, so what I'm going to do is full adder 0. Let's say I'm going to partition this with m equal to 4 bits, and I'm trying to do 16-bit addition. That's the example we are going to consider. Full adder, then a mux Cin. So this P is simply going to be P0, P1, P2, P3. I select for the mux, and if it's in propagate mode, I'm going to create this. This is Cout. The sum is still going to come out, by the way, like this. Okay, that nothing changes there. This is S0, S1, S2 and S3. Okay, so what I'm going to do is I'm going to take this circuit and now repeat it n number of times. Okay, so let me just copy this schematic so that I save some time here. Okay, may not be a good idea. Let me redraw that because I've already indicated the critical path there. Okay, so each block, I first need to create the generate and propagate signals, right? That's going to take 1 unit of time. So that is the first block that I will put, GP. Okay, and this is going to take 4 bits, A0 to 3 and B0 to 3. Okay. Then I have a full adder. Okay, and then what I'm going to do is, this is my C in. I want to put a bypass mux here. Carry out will come from here and C in will come from here. This is my propagate signal. P equals P0, P1, P2 and P3. Okay, of course from here I will get the sum S0 to 3 as well. G and P. Now I will repeat this block. G comma P, A 4 to 7, B 4 to 7. Again my full adder, 4-bit full adder chain this is. Okay. Then again I'll put a mux here. P equal to P4, P5, P6, P7. Right? This is my thing. Carry out, that will go here, and this will also come for the bypass. Okay, this is 0, 1, 0, 1. This block here is what I showed in the previous slide. This one. 4 ripple adders with 1 multiplexer in the end. Okay. So like this I can take it on, and the last stage will basically be again GP. A 8 to 11, 12 to 15, right? B 12 to 15. Okay, again I have a full adder. C in, bypass, C out. And this is S 12 to 15. Okay, this is S 4 to 7. Okay. This is the architecture of the carry skip adder. At every M bits, we are going to try and skip, right, the carry out part through that bypass multiplexer. Okay, so now let's define some terms here. Let's say TGP is equal to time to generate, time to create, generate, propagate signals. Which means that this operation going from the first block, the time here is TGP. All of them happen in parallel. Okay. Then of course I have T sum equal to basically time to create sum. T carry is at that circuit level for a full adder, how much time it takes to create sum, right? This is full adder time to sum, full adder time to create C out. Now there is a bypass multiplexer that I have put in the path. So let's say that this time is T bypass. Mux time. Okay, so with that I think we have covered all the blocks. Now only thing we have to figure out is what is my worst case delay and what mode of operation should each of these 16 adders be in. Can, for example, bit A5 and B5, that full adder, can it be in generate mode? Suppose it is. Suppose it is. Right? Then, of course, from G5 to bit 7, it has to propagate. Right? After that, it's going to be in bypass mode. My worst case. Basically, if A15 and B15, that full adder happen to be in generate mode, then my carry is ready immediately. Right? It's the same thing as the ripple adder. If my last stage is in generate mode, then there's no question of that being the worst case delay. Carry out is ready immediately. So it has to be somewhere earlier. How much earlier? We said it has to go all the way to the first bit. So I'm asking similar questions here. Can any bit in between 0 to this thing be in generate mode? Yeah? You agree that it's very similar to the ripple adder here. Any bit in between being in generate mode cannot be the worst case delay, because that will have a lesser time to propagate through now. Correct? So therefore, all these adders in between have to be in propagate mode. Right? I have 4 adders, so I'm going to put all of that here. Propagate mode. Okay. Now what about the first stage? Obviously, 3 adders, A1 to A4, A3, had to be in propagate mode. What about the first adder? A0, can it be in propagate mode? Why? Yes, if the A0, B0 adder happens to be in propagate mode, then this signal will go high and bypass the carrier in. Therefore, that cannot be in the propagate mode, that has to be in generate mode. My question is, why can't the other guys in the other stages, why is that not the worst case? Why is GPPP not the worst case for the other stages? Because if you generate in between there, then the carry has to propagate much lesser distance, just like a ripple adder. Get it? So therefore, you have to first learn to identify this worst case condition, propagate or generate. After that, we can write out the critical path delay very easily. Okay?
Dependent on that, then it means like the arrival time of output also will not like the input is changing, but the output is like not it's not changing for that particular case.
Correct.
So the arrival time of output we don't include that case.
Correct. Because it's a max kind of thing, right? So therefore, the worst case guy will determine it. Yeah. Okay. So now can we write out the delay of this, the critical path delay of this circuit? T carry skip. Of course, first thing is you have to basically create this TGP. Right? It takes time to create the generate propagate signals. What about the delay through this first adder? The delay has to literally, if you look at the critical path, it has to go through this adder like this, because it has to propagate, it has to ripple the carry through that first stage. Correct? So what is the ripple delay there? This full adder block here is a regular ripple full adder. It has only 4 bits, that's all. How long does it take to, what's the rippling delay? Yeah, so basically T sum plus, yeah, so we said in general this is going to be m bits and the number of stages will be n by m. Right? So therefore this has to be what now? M minus 1 T carry. Sorry. Plus, we have arrived till here. Now I have to, whether the mux is bypassing the carry or it is taking the carry from the rippled string, you have to go through the bypass mux. Right? In the first stage, you are rippling through the thing and you have to go through the bypass mux. From second stage onwards, there is no rippling. It's only bypassing. Right? So that is T bypass. And how many bypasses? N by M. Good. Let's write that down. Okay? Now question is, if you bypass the last mux, this mux, what are you doing? You are basically telling me when C out will be ready. This time that you have told me, T GP plus T sum plus M minus 1 T carry plus this is basically the time that it's going to take for the carry out to be ready. But what about these sum bits? All the bits have to be ready, right? Here I didn't worry about that because while the carry was rippling through the other stages, these sum bits will evaluate. So there is no problem there. I don't have to count that. But the question is for the last stage alone, how will you handle this correction? Exactly. You have to allow this to go through n by m minus 1 bypasses. Right? And now what should be the delay for the last stage? Yeah? Plus T sum. So plus T sum into T. Okay. Bypass. Yeah. That's also a very good point. Good point. So his point is that in the first stage, we don't have to, the ripple worst case time that we derived earlier for the ripple carry adder was for both sum and carry to be ready. T sum and T carry. That's why we said it should be T sum plus M minus 1 into T carry. But in the first stage, when I am rippling through, I don't have to wait for T sum to evaluate. I just have to wait for the carry out to be ready. While that propagates, this T sum will evaluate. So therefore, this also is wrong. It has to be M times T carry. No, M T carry. It's not M minus 1 bits. All the m bits I'm propagating. First bit? No, that's okay. It's first bit is generating the carry, right? It takes t carry time to generate that carry. See, whether you generate or propagate, you have to perform a logic operation to get that. See, the carry out will be G into C in, right? I mean, it'll be G. No, what I'm saying is, hold on. What I'm saying is that carry out is equal to G plus P into C in. Correct? Now this is going through a logic gate. It doesn't matter if G is just appearing at C out, but it still has to go through that logic gate. And that we are saying is going to take T carry. Whether you are doing propagate times C in or just taking G to the output, right? You have to go through that inversion logic, right? You have to add an inverter, you have to do. So that is going to take T carry. So therefore, this has to be only M times T carry, right? Plus now the last stage has to be what? Yeah, M minus 1 T carry plus T sum. Now we'll check if we are right. Yes, TGP MT carry plus N minus M by M minus 1 T bypass plus M minus 1 T carry plus T sum. Okay, clear? Since this is the first architecture, I am doing it very slowly. I'm doing it really slowly so that we go through the obvious mistakes and correct them. That's the aim. Okay.